Okay, in this section in 5.2, this is where we now start to connect these properties of the unit circle with trigonometry functions, namely sine, cosine, and tangent. Sine, cosine, and tangent, those are the three out of the six total trig functions, but these three are the most core trigonometry functions. And when I was writing these lecture notes, I could hear a chorus of students asking me in one breath, well, where does sine, cosine, and tangent come from? And to be honest, that's been kind of a nagging question of my own. So I thought I would look into it, study it a little bit, and see what I could find. So this is what I found, and I tried to summarize it as best I can. And I felt it was interesting enough to just include it. So here we have the origin story of trigonometry ratios and the art of dialing. So Persian mathematician Muhammad ibn Musa al-Khwarizmi, forgive me if I butchered that pronunciation, was born around 780 AD. His name includes al-Khwarizmi, which can mean the native of Khwarizm. In his era, Khwarizm was part of Greater Iran, which is now part of Turkmenistan and Uzbekistan. Around 820 AD, al-Khwarizmi wrote the compendious book on calculation by completion and balancing. Okay, I would really embarrass myself if I tried to translate that, but here's the translation in I guess this, I'm embarrassed to say, Persian language. Pardon me, but the original uh, title of this book has the word al-Jabbar in it, and al-Jabbar in the title of this book later became the origin of the word we use today, algebra. So we get algebra from the title of this book, which had al-Jabbar. And hence, Muhammad ibn Musa al-Khwarizmi is credited as the father of algebra today. When this book was translated from Arabic to Latin, the Latin word algorithmy is used in the title, and that led to the term algorithm, which we use today. And you see the word algorithm used a lot in computer science. So the original works of Al-Khwarizmi uh, do not survive today. But translated copies of his book, of the compendious book on calculation by completion and balancing, has been translated into Latin by two or three of the most noted translators of the 12th century. These translations include tables of sine theta to three decimal places and 12 cotangent theta to one fractional place. Um, so, again, it's interesting to kind of know that, algebra and algorithm, come from the Middle East, and namely parts of what were once part of Iran. But I thought, let me trace this back as far as I can go. And here, what we've got is a chronology and evolution of the concept of the word sine that we think of today. And it actually goes all the way back to Turkey between 100 and 200 BC in the Greek language. And this was the word that represented what would be later be called sine. And in Greek, this is the word chord, okay, which translated is a string of gut. And then this idea kind of migrated from Turkey to India between 240 and 550 AD, and that was in the Sanskrit language. So it changed from being Greek to Sanskrit, and this was the word that it was translated into. And this means bowstring half. So bowstring half, so if you think of a bow like a bow and arrow, here is the entire bowstring, but bowstring half would just be this part right here. Oops, erase that. And, that word, ja'ard, I'm guessing, was then later converted into jia, which then was converted to jiva. Again, I'm probably slaying these pronunciations, just doing no justice to them at all. I'm trying. Um, and then this idea, of a bowstring half, I think before traveling further, so we have jia, which means bowstring half, and then we have koti jia, which means complementary of the bowstring. And complementary of the bowstring was actually this part. So the angle that's made by the bowstring half and the complementary would be this angle here. Okay. And the length of this side is what we would later come to know as sine. And the length of this side is what we would later call cosine. Okay, but let me keep going with this. Um, so this idea left India, went back to Persia. We're now in 700s AD. It was translated into Arabic, and Jiva was translated into Jiba. And then Jiba was translated into these two words, which meant cove or bay. So you can imagine maybe the bow itself being like a cove or a bay near the ocean. And it was here that in 820 AD, the compendious book on calculation by completion and balancing was written by Al-Khwarizmi. And then this idea traveled to Europe sometime around the 1100 AD, and it was translated into Latin, where this Arabic JB was translated into JB. And these two together were translated into the Latin word sinus. Okay, and sinus means curve, fold, bend, bay, or hollow. So you think of like the sinuses in your nose, your sinus in your head is like this big cavity. It's a hollow part in the front of your head. And then when this Latin word sinus was then converted again in Europe to English, then it was converted into the word sine and codified into mathematics by the Swiss mathematician Leonhard Euler, and then included in the first printed book with this use of the word sine. And the book was called The Art of Dialing, written by Thomas Fayle in 1604 AD. So you can see that, this idea of sine existed, maybe 1700 to 1800 years earlier? 1700 to 1800 years earlier, before it was printed, in a book. So, that's interesting. Um, so let's look at this art of dialing. So maybe one of the first printed, and I have to say English books, I didn't stipulate that up here. I mean, it had been printed in other languages, okay? But in terms of being printed in English, um, it was done by Thomas Fayle, and it used sign tables that Thomas Fayle created. And it's published in either 1604 or 1583. And I got 1583 from this number that was in the book there, but other sources cite it as being 1604. And this is, the cover of the page. That's what the cover of the page looks like. And here's a couple of pages from the back. This is the very end. And the very end actually has some example problems. Okay. And you can actually read that. It's because it's in English, it's somewhat intelligible. Just the grammar is a little weird, something we're not used to. Um, and so I took this part from the book, and this is what it says. It says the elevation of the pole at camber is 52 degrees. Pole sign I desire to know, therefore resolving one of the degrees into minutes. I enter, I couldn't figure out what that was, table with 51 degrees, 60 minutes. In the common area, I find the sign to be 78801. Right? Okay. Yeah. So the way that I translate that is calculate the sine of theta, where theta is your angle, and that's 52 degrees. Given that 1 degree is equal to 60 minutes, you want to convert 1 degree in theta into minutes. So 52 degrees is equal to 51 degrees plus 1 degree, and you convert that 1 degree into 60 minutes. So you've got 51 degrees and 60 minutes, and that represents 52 degrees. Okay. So you have degrees and you have minutes. So you go to the table at the back of the book and you find where the degrees is 51. Okay. And then you find the row where the row is 60. And so you come down from 51, you go over from 60, and this is the sine of 52 degrees. And you can see if you use a modern day calculator and you calculate the sine of 52, you get 0.78801, which is the same value that's in this table. So I find that pretty remarkable. And a further question would for me is how did they get these numbers, you know, without a calculator just to do it for you? How did they manually go about doing it? That's something I would like to know. And maybe I'm embarrassing myself because, other mathematicians just go, oh, yeah, this is how you do it. But I haven't learned that yet. So I'm going to admit to that gap in my knowledge here. Um, and just for fun, what would be the sine of 30 degrees? So you would take 1 degree of that and take it down to 29. So you look on the page where D is equal to 29, and you convert 1 degree into 60 minutes. And you come down from 29 and you come over from 60, and what you get is 0.500 or 1/2. And we know if you look at your unit circle or if you've memorized it, the sine of 30 degrees is 1/2. So I find that really interesting and amazing. Um, where sine and cosine came from. It came from a real practical example of looking at a bow and the string of a bow. And when you draw the string back, that distance traveled, makes up a length, and then the bowstring half makes up another length. And it was this bowstring half which went through a lot of iterations to finally get to the word sine that we use today. And the complementary of the string is called the cosine. So this side here would be the cosine. And it's this length and this length, which actually becomes part of our unit circle, which would be something like that. So our unit circle would just keep going around and around and do something like that. So that's kind of where that comes from. So this is where the parameters of the unit circle are going to tie in with trig functions here. So I think this is a good time to stop with this history lesson. Okay, we'll stop here.